All right, hello and welcome back to another Mathcounts meeting. So today we are continuing 2010 Nationals, and we are currently on number 14 Sprint. So we have, what is the volume in cubic centimeters of a right rectangular prism with all integer edge lengths and faces having areas of 30, 180, and 24 square centimeters? So I don't know. So if you don't know how to do this problem already, we can just start by just thinking of our right rectangular prism, and then thinking about like our integer edge length. So we can just call that some variables like x, y, and z. And then if we have if we're given like faces of areas 30, 180, and 24, our right rectangular prism is only going to have like three types of faces. And so like each of these areas is going to correspond to one of these faces of a right rectangular prism. So I don't know, I'll just say 30 is here, 24 is here, 180 is here. Basically, each of these is going to correspond to a different product of our two variables, right? So then I can say xy is 180, yz is 30, and xc is 24. And then we want to find the volume, right, which is xyz. And then now, while you could, solve this whole like system of equations, right? You have three equations, three variables. You could go through it all and solve for what x, y, and z actually is, and then plugging it back into here and finding the volume. Yeah, you can do that, but there's actually a neat little trick you can do here if you have like all these product pairs and you want like this whole three variable product. And what you can do is you can multiply all of these pair of products together. So this is going to equal 180 times 30 times 24 because the xy corresponds to 180, yz corresponds to 30. We set it up that way. And then you can see on the left side, we're going to be left with, we're going to have two x's, so x squared, we're going to have two y's, so y squared, and we're going to have two z's, so z squared. And you can notice that, this is the exact square of what we wanted to find, right? So then all we have to do is square root both sides. So then we have x, y, z on the left side. And then on the right side, we're going to be left with the square root of 180 times 30 times 24, right? So basically now we shortcutted all this, and now we've already found an expression for what our volume is. And we didn't have to solve for what the variables actually were at all. So then, let me just solve this. So I'm just going to take the square root of this, and I want to take out any square factors I can find. So, 180 is going to be, well, I can take out a 30 from 180. So 180 is going to be 30 times 6. This is going to be times 30, and then I can separate 24 into 6 times 4. So then I can take out these two 6's into 1 6. I can take out these two 30's into 130, and I can take out this 4 into a 2. And then my volume is just going to be 12 times 30, which is 360. Oh, and check units. This is all in square centimeters, and it wants in cubic centimeters, so we're fine. And then we're on number 14, so yeah, that's our answer. So, so this kind of like question type, like this exact question type, actually comes up like kind of frequently in I don't know, general competition math. So, like this is kind of like, I don't know, this is kind of like a well-known trick that that competition math tests you like now and then. So I don't know. It's just like uh kind of like get to know this trick, I guess, if you don't know it already, because it's, yeah, actually kind of comes up a lot. Um okay, but yeah, anything you want to say there, Bill?
Yeah, like uh, dealing with like the surface area of size like this, and also like sometimes the sides. They'll deal with size with like volume. Just multiplying all of them out like this. It happens a lot.
Yeah. Yeah, and then so yeah, so like if you already knew this trick, and you want to solve this problem like really quickly, like all you have to do is just take the product of all of these and square root it, and then you can just do that really fast. Just take out square factors and stuff. So yeah.
Yeah, and like sometimes it'll be like it might be you have to like square one of them or something. Like you have the three sides and you have to square them, but like
Yeah.
this type of question comes up a lot where it deals with like sides of a prism or something, rectangular
Yeah.
prism.
There's also another shortcut thing. I don't think it comes up as much as this. I've only seen this like once during a UIL calculator test actually. But maybe it comes up more, but I like haven't seen it. Basically, it's like instead of having the areas and you want the volume, you have like each of the faces diagonals and you want the like internal big diagonal thing. So then, to derive like the trick, I guess you could see, let's say we have XYZ again, and then we're gonna have like x squared plus y squared rooted is gonna equal something. Um, and then y squared plus z squared rooted is gonna equal something. These are our diagonal lengths. And then the root of x squared plus z squared is going to also equal something. And then the big diagonal length is going to be x squared plus y squared plus z squared. So basically, if you're given the three diagonal lengths, what you can do as a shortcut instead of like finding all the x, y, and z and stuff is you can square each of the diagonals. So I'll call the diagonal lengths a, b, and c. You can square all the diagonal lengths and add them together, and then you see that you're going to get like x squared plus y squared plus y squared plus z squared plus x squared plus z squared. And then if you have that, you're going to get just x squared plus y squared plus z squared. Oh, sorry. The large diagonal length is going to be this square rooted. So then you would take the sum of all of these, you square it, and then you have it to get just x squared plus y squared plus z squared, and then you just square root it. I feel like this is kind of like a little bit more steps than this one, but yeah, I'll also maybe know this one, I guess. Okay. Anything you want to say for that, Bill?
Oh yeah, I guess just be. Just, oh yeah, that's just
But
another
also
operation with like the sides.
generally like be out for the look of like like if you're given like some kind of equations, like see if you can manipulate it just to get like what you want to find instead of having to like find all the
Yeah,
variables.
just like be comfortable with working with like multiple variables like this.
Yeah. Okay, I think that's good for that one. Okay, number 15. What is the largest value of x? It's just that 100 factorial is divisible by 2 to the x. So we want to divide 2 to the x into 100 factorial, and we want x to be the biggest power as it possibly can be. So then we're just looking for like what are the total number of factors of 2 that are in 100 factorial, right? Like um, however many factors of 2 that are in 100 factorial is what is the maximum x that 2 to the x can divide into 100 factorial into, right? So we're going to want to look for that. And then how are we going to look for that? Well, we have to know what a factorial means, right? 100 factorial is going to mean like we have 100 and we're going to take the product all the way down all the way to 1. And then, so how are we going to figure out how many factors of 2 are in here? Well, we can think about all of the even numbers are going to contribute 1, 2. So we can count them like all once. So basically, like I can think of my 2, my 4, my 6, my 8, all the way to my 100. All of them will contribute one factor of 2. But that's not like just the end of it, right? Because if you think of like any higher power of 2, something like 4, this doesn't just contribute one factor of 2, this contributes two factors of 2, right? So we can't just only count this once. Um, we would have to count any factors of 4 twice, right? So then, what if we did that? So then what if we counted all the factors of 4 again. So 4, 8, 12, 16, all the way to 100. So these are factors or multiples of 4. Sorry, these are multiples of 4. So we know that they're going to contribute 2 factors of 2, right? So we need to count them twice, right? And we know we already counted them once in here, so we can just count them once again in here, right? So then that way, the ones that contribute 2 factors of 2 are counted twice, once in this and once in that, and the ones that only contribute 1 factor of 2 are just counted once in this expression, right? But still, this isn't the end of it, right? Because if you think about it, some higher powers of 2 are going to contribute more than just 2 powers of 2, right? So if I look at 8, 8 is not going to contribute 1 or 2 factors of 2. It's going to contribute 3 factors of 2, right? So then we're going to have to go up and count that again, right? Any multiple of 8, it's going to contribute 3 factors of 2. So we need to count it 3 times, right? And we already counted it once in here, once in here. So what we can do again is now list all the multiples of 8. This goes up to like 96. And then we count all these again because they contribute 3 factors of 2. And maybe you see a pattern here now. And it's basically what we do is like we list out first just the multiples of 2, and then we list out the multiples of 2 squared, and then we list out the multiples of 2 cubed. And that's basically what we do in these type of factorial like factor problems and stuff. So we're going to keep on listing these lists of multiples of 2 to the power or something until like we get to a big number that is more than 100. So then we're going to go to 16, and then this is going to go up to 96. I'm just going to put dot, dot, dot. And then we're going to have 32, and then, oh, what the heck? I don't care about. Remind me later. Oh, what the heck? I'm sorry about this. Okay, that was not. Okay, I'm sorry about that. I don't know what just happened. Okay. Okay, so then we list out our multiples of 32. So our biggest is going to go up to like 96 again. And then we have 64, and then the next multiple of 64 is 128, but we only have 100 factorial, so we just have 64. And then our next power 2 is going to be 128, but that's too big, so we're not going to have any multiples of 128 in our 100 factorial. So now, like we said before, we want to count like each of these number groups once for every number in the number group. So this list of even numbers, 2 is 1 times 2, and 100 is 50 times 2. And all these numbers in between are just going to be like 2 times 2, 3 times 2, and so on. So that means we can just count it by whatever this number is, right? Since we're just like counting this 1, 2, 3, and so on. So then there are going to be 50 numbers in this group. And we can also do the same thing for all the numbers, right? So I can say this is 1 times 4, this is 2 times 4, and then this goes up to 25 times 4. So then there are 25 numbers in this list. And then, all these are always going to start on like 1 times 8, and it's always going to go like plus 8, right? So then all I had to do is look at what this last number is, like what multiple, like what number multiple of the last number is to our first number, and then that's going to be the number of numbers in our list, right? So 96 is the 12th multiple of 8. So then there are going to be 12 numbers in this list. 96 is going to be the 6th multiple of 16. So then there are 6 numbers in this list. 96 is the 3rd multiple of 32. So there's going to be 3 numbers in this list, and there's just 1 number in this list. Okay, and then we add all this together. So then we have 75 from that, and then we have 87 from that, and then we have 93 from that, and then we have 96 from that, and then we have 97. So it all adds up to 97, and that is our answer. So yeah, if you've never seen like these factorial, like you're getting some kind of you're trying to find like the number of like factors factorial has or something, this kind of problem actually comes up fairly a lot, I would say. I have seen this a lot in science school actually, but Um, yeah, basically what you do is you just list all of the you just list like the powers of the factor that you're looking at, and you want to add up all the number of numbers in each of these groups. Okay, anything you want to say for that one, Bill?
Uh, uh, Not particularly. Yeah, I think I'm good.
Okay, give me 1 second. Okay, let's move on to number 16. How many positive three-digit integers contain at least one 3 as a digit, but do not contain a 5 as a digit? Okay, so, we're just looking at three-digit integers, right? And it says that, we're looking for the ones that are contain at least one 3 as a have at least one 3 as a digit somewhere, but does not contain 5 as a digit. So for this one, I feel like casework is pretty effective, because we're not going to have many cases for where threes are going to be, because we're just working with three-digit integers. There's like and like they contain at least one 3. There's not going to be a lot of casework for that. And I don't know. You probably do this also without casework, but I don't know. It's also going to be a little bit weird. So I think casework is fine for this. So let's just do casework. So basically, we're going to do casework depending on where our threes are located, and like yeah, basically just where threes are located. So first, I'm just going to do the simplest case, which is if all the digits are 3, right? So then here we have a three-digit number that has at least one 3 as a digit. And I don't know, this is just one of our cases, right? And you can't have like anything else in this case, and then this case is just going to be a 1. So I'll keep a tally mark here. So then this one is going to be like this one is going to be 1. Okay, and then what if we have two threes, and then this spot is not a 3? Well, this is also going to be the same as if we had 3, and then this spot is not a 3, and then this is a 3, right? Because both these positions are going to be the tens of one place, and they're going to be like they can have like the same digits in them, and we don't care about like the tens and ones place individually, so these are going to be like the same case, right? But the case where we have a non three digit in the hundreds place, and then threes here, these are not going to be the same case, right? Because the hundreds digits, it can have, or it can't have 0, where these places can have 0, right? So this is going to be a separate case from these two cases. So I'm just gonna put this one here, and then I'm just gonna say like we need to multiply this by 2 at the end. Okay, so then how many ways can we have this case? Well, we just need to think about how many ways we can have this digits, or how many digits we can have in this place, I guess. So we can't have a 3 in that place, because then it would just be this case, right? And this case, we're specifically saying that this digit is not a 3. And it also can't be a 5, because none of our digits can be 5s. So then there's no other restriction. So usually there's 10 digits that can be in here, but here we only have 8. So then it's going to be 8 cases, but we need to multiply by 2. So then we're going to have 16 cases for that. And then what about our hundreds 3 3 case? Let's just do that now. Um, So like I said, we can't have a 3 or a 5 in here for the same reasons that we can't have a 3 or a 5 in here. And then we also can't have a 0 in the hundreds place because then it would be a two-digit number. So then we have 7 cases for this, and we don't need to multiply by anything because it's just going to be the only case we can apply this to. So then we're going to have 7 for that. Okay, and then now we can do 3 and then not a 3 and then not a 3. And we're just going to have one case for this. And then we're going to have 2 cases for not a hundreds digit or not a 3 in the hundreds place, and then a 3, and then a not a 3, and then a not a 3, and then a not a 3, and a 3, right? Because in both these cases, you know, we have not a 3 in a hundreds digit, and then in our other 2 digits we just have like the 3 and then a not a 3. We don't care about like the placements in those two digit places because like they're treated the same, right? So these 2 cases are going to be the same. Okay, so let's just do this one. So again, for both of these digits, we can't have 3 or 5, but we can have all 8 other digits. And there's no other restrictions between like what these two can be. So then it's just going to be 8 times 8, which is 64. And then so let's just do like one of these cases and then multiply by 2. So again, the hundreds digit, we can have 7. We can put 7 digits in that, and then our ones or our tens digit, we can put 8 numbers into that. So then we're just going to have 7 times 8, and then that's going to be 56, and then we're going to multiply that by 2 since we just counted this for one of these, and they're the same case, so we're going to count it for both of them. So then we have 108. Okay, and then we're just going to add all these numbers together. So 16 and 64 is going to be 80. And then 80 and 108 is going to be 188. And then we add an 8 here. And then that's going to be, 196. Uh-oh. Uh, I'm 4 off.
Hmm. 4 off. Okay. Oh. Um, you did
Yeah.
you did
Oh, this is
56. That should be
this is yeah,
112.
this is a 112. Okay, yeah. So then that's gonna add like 4 to what we had before. So then that's gonna be 200. And yeah, that is our answer. Okay. Anything you want to say for that one, Bill?
Oh yeah, just casework, I guess. Nothing really much. If you try to do it without casework, there's like a lot of overlapping stuff.
I mean,
It would get
I feel like
messy
if you
real quick.
just try I feel like if you just try to do it like without casework, then you're just like you're gonna end up doing casework. I don't know.
Yeah,
It's
you're
just gonna
gonna
be like
because
casework.
if you try to do it without casework, you're going to have to account for all the ones that you repeat accounting. So
Yeah, and
like
then it's basically
in
just
essential,
casework.
yeah, essentially you're going to do casework for because each case you're going to be repeating a different amount of numbers. So you're essentially doing casework again.
Yes. Okay. Let's move on. Number 17. In order, the first 4 terms of a sequence are 2, 6, 12, and 72, where each term beginning with the third term is a product of the 2 preceding terms. The ninth term is 2 to the a times 3 to the b. What is the value of a plus b? So we have like a product sequence here. So, like a product Fibonacci sequence thing where like, you multiply 2 numbers and you get the next number. So 2 times 6 is 12 and 6 times 12 is 72. And then you want to find how many factors of 2 is in the ninth term and how many factors of 3 is in the ninth term as well. Well, what we can do here is we can just keep track of all these terms and what their how many factors of 2 and how many factors of 3 they have, right? So like 2 is going to be 2 to the 1 and 3 to the 0, and then 6 is going to be 2 to the 1 and 3 to the 1. And then you can see like whenever you multiply these two numbers together, you're going to be adding their powers of 2's and their powers of 3's respectively, right? So our next number is going to have 1 plus 1 factors of 2, which is going to be 2. And then the next number is also going to have 0 plus 1 factors of 3. So it's also going to have 1 factor of 3. And then you can see that's going to multiply to just 12, right? And then you're gonna keep on doing this, right? So you're gonna add these factors again. That's gonna be your number of factors 2. You're gonna add this again. That's gonna be the number of factors of 3, right? So then you can see if you look at the the exponent in each of these factors, then it's just following like a regular Fibonacci sequence, right? And then you can just go on to that. We're just going to the ninth term. You can just calculate it by hand. Up to the ninth term, it's not that far away. And then you can just do that, right? Just do two Fibonacci sequences for each of these and just calculate it up to the ninth term. So first I'll do the 2 sequence, right? So first we start with 1 and 1, and then right, this is just going to be a Fibonacci sequence, right? So then my third term is going to be 2, my fourth term is going to be 3, my fifth term is going to be 5, and then 6 is going to be 8, 7 is going to be 13, and 8 is going to be 21, and then 9 is going to be 34. Okay, and then my factors of 3 is going to start at 0 and then 1, and then this is going to add up to 1 and then 2, and then this is actually just like the same Fibonacci sequence we have for the factor of 2, except it's like except it's 1 term later. So then I can just predict that this is going to go up to 21. Okay, and then then we know our ninth term is going to have 34 factors of 2 and 21 factors of 3. And then we just want to find what a plus b is, so that we just add these two, and then we have 55. That's our answer. Yeah, that's our answer. Anything you want to say for that one, Phil?
Yeah, like the answer kind of hints at like the method they want you to use, like the answer itself. It's pretty obvious from the answer they want you to put everything in terms of like powers of 2 and 3, I guess. And if you put everything in terms of powers of 2 and 3, that's a pretty easily noticeable pattern.
Yeah, you just have to notice that, like, I don't know.
Also, like in the problem
Uh,
itself, it says product of the 2 preceding terms. So you might think like, I don't know, that kind of sounds like Fibonacci. I wonder if I can modify this Fibonacci sequence.
well, yeah. You just have to notice, like, when you're taking the product of the two terms, you're just doing like you just have to notice that it's just Fibonacci with the exponents, and then you can just do it like that. Okay, let's move on. Number 18. Two cross sections of a right hexagonal pyramid are obtained by cutting the pyramid with planes parallel to the hexagonal base. The areas of the cross sections are 216 root 3 square feet and 486 root 3 square feet. The two planes are 8 feet apart. How far from the apex of the pyramid is the larger cross section? Okay, so what we have here is first we have a right hexagonal pyramid. So, hexagonal pyramid means we're going to have a hexagon as a base. And then that's not the best hexagon in the world, but sure, we can just use that. And then the right pyramid just means like, if we have the height up here, this is just going to make a right angle with our hexagon plane. And then, our pyramid is just going to connect to it like that, right? And then what's going to happen is we're going to cut the pyramid with planes that are parallel to the hexagonal base. So like maybe a plane like through here and then a plane like higher up. It's kind of weird to look at this because it's 3D and I'm trying to draw it in 2D, but yeah, just imagine it. And then, then you have like some area of the bottom hexagon cross section, and then the area of the top hexagon cross section. And then the planes are 8 feet apart, and you want to know how far is the larger cross section, which is at the bottom. How far is that from the apex of the pyramid? And it's pretty weird to think of this like all in 3D. Usually for 3D problems, you don't want to think it in 3D. You just want to like simplify it to 2D because you can like do geometry and all that stuff like a lot easier. So I want to try to make this somehow 2D. Well, one way I can visualize this in 2D is if I look at the pyramid like head on and just like flatten it out basically. So then I'm just gonna be looking at my pyramid like this. So then this is gonna be the apex. This is gonna be the apex, and then this is gonna be my base. And then so one of my planes is gonna cut through like here, and one of my planes is gonna cut through like here. And then this is gonna be 8 feet apart, and I want to know what like this total distance is. And so, this is a kind of a good way to look at it because, we get the 8 feet between the planes and we also see what we're trying to go for. And then, so, what the area of this, you know what the area of this hexagon thing is, and you know what the area of this hexagon thing is. And, obviously with the areas of these two hexagons, that's not very useful, right? Because we're trying to find like lengths and stuff. But you can just convert that into a ratio of the lengths of the hexagons, right? Because all of these hexagons are going to be similar, right? Because they're all like on the same pyramid, right? Like if you take the same cross sections of a pyramid, you're gonna get like similar figures to the same base, right? So they're all gonna be similar. So, if I know that my two hexagonal cross sections are similar and I know what their area ratios are, then I can also find what their length ratios are. And then, length ratios might help me a lot more in this problem because I'm trying to find lengths and stuff, right? So, so from my largest to my smallest hexagon, my area ratio is going to be 486 to 216, right? And we talked about this a lot before. If you have like a 2D ratio of something, and you can just square root it to get the 1D ratio of the shape. But the shapes have to be similar, but they are here. So basically, we could just square root this ratio, and we can get the ratio of their lengths. So we should probably try to simplify this. So we can take out a 6 from top and bottom. So then we're going to have 81 over 36. We're going to take the square root of that. And then 81 is just 9 squared. 36 is just 6 squared. So then this is going to simplify into 9 over 6, which is also just, or sorry, this is going to, oh, wait. Oh, yeah, this is going to be 3 over 2. So now we found out that the length ratio of our larger hexagon to our smaller hexagon is going to be 3 to 2. Okay, so then then I can just call like this length something like 3x, right? And then I can just call this length something like 2x because I know the ratio of this length to this length is just going to be 3 to 2. And then you can see that we have similar triangles here, right? We're going to have a similar triangle right here, and we're going to have a similar triangle right here, right? Just because like these two planes are parallel, right? So these two lines are going to be parallel, and these two lines, this line and this line, are also just on the same like height line, right? And these lines are also on the same line, right? So basically, all of the lines are parallel with each other. So then all the angles are going to be the same, and then so all of those are similar triangles, right? And then so then you can see like if we have a ratio from this side that is 3 to this side, that is 2. We're also going to have a ratio from this whole side being 3, and then this smaller side being 2. So this is kind of messy here, but like I can call let me just call this whole height thing right here y, right? And then I can call the smaller height thing right here y minus 8, right? Because I know that this the distance between the planes is 8, right? So then this is going to be y minus 8. So from the similar triangles, if the bigger triangle, if the ratio of the bigger triangle to the smaller triangle in lengths is 3/2, then we can see that y over y minus 8, which is just like the heights of the triangles, is also going to be equal to 3/2. And then here we can just solve for y, right? So cross multiply, we're going to have 2y equals 3y minus 24. And then we can bring y over here, and then we can bring 24 over here. So then we can see that y is going to equal 24. And then you can see that y is just what we wanted to solve for, right? It was a distance from the apex to the bottom hexagonal plane. And so yeah, this is just going to be your answer, 24. And yeah, that is our answer. Right, sorry, and that is the correct answer. Anything you want to say for that one, Bill?
Yeah, like this concept comes of a lot of like relating proportions between 3D, 2D, and 1D. And it's always just
Yeah,
like 1D is going to be 1, 2D is going to be that squared, 3D is going to be 1D cubed, and yeah, if there's a 4D, it's probably 1D to the fourth. If there is a four, if you do work with 4D somehow. But yeah,
yeah, yeah. We talked about this a lot, but yeah, if you, I mean, it's just pretty simple stuff. It's just
yeah,
like, if you have two like objects that are similar to each other, then like all of their 1D, 2D, and 3D like uh measurements, I guess, like are gonna be in like ratios, and these ratios are gonna be like corresponding to each other depending on the dimension they're in. So like if you wanted to get from the 1D ratio to the 2D ratio of the objects, you can just square the 1D ratio. And if you wanted to get to the 1D ratio to the 3D ratio, then you just cube whatever that ratio is. I mean, that should also be pretty intuitive from like stuff, I don't know, you've been working with, right? Like if you have the radius of a circle that is double, then the area is going to be quadruple, right? Then you just like square whatever that radius ratio was to find that area ratio. But yeah. Okay. We can move on to the next one. Number 19. 4 dimes and 4 pennies are randomly placed in a row. What is the probability that the first and eighth coins are both dimes? Express your answer as a common fraction. Okay, so um, so one way we can calculate the probability of this case happening is we can find the number of like permutations that we can have in this case, and divide that by the total number of permutations that we can have in our total case, right? So the case that we are looking at is that the first and eighth coins are both dimes, and then and then the stuff in between is going to be 2 dimes. Sorry, I'm going to have capital D's here. 2 dimes and 4 pennies somewhere in here. So this is going to be what we're looking at. So what we can do is we can find the total number of permutations that we can have for this, and divide it by the total number of permutations that we have for like our total case. And our total case is just given 4 dimes and 4 pennies, and they're randomly placed in a row. So then you're just looking at a row with 4 dimes and 4 pennies. Okay. So the number of cases for what we're looking at here, the two dimes here, they're already like, I don't know, in place. We're not really gonna do anything. And just like to find the number of cases of this, all we have to do is just find how many cases we can arrange like this middle part thing right here, right, with the two dimes of four pennies, because like they're always going to have the dimes on the end, and that's not going to change like how many cases we can have for all of this, right? So then how many ways can you arrange like two dimes of four pennies into row six? Well, then we don't have any other restrictions with that, so that's just going to be like that's just going to be six choose two. Um, that's like basically by definition. But yeah. So six choose two. Okay, yeah. Let me write that down. So yeah, the number of permutations for our numerator here is just going to be six choose two, and then our denominator is going to be how many ways can we arrange four dimes of four pennies into a row of eight. Well, that's also just going to be eight choose four. So now we just have to calculate this. So six choose two is just going to be six factorial over two factorial times four factorial, and then eight choose four is just going to be eight factorial over four factorial over four factorial. And then I can take out, I don't know why I'm working like right to left. Sorry about that. I'll just bring this down, I guess, and I'll have some space. So I can take out a four factorial from the six factorial, right? Like the six factorial is like six times five times four times three times two times one, and this bottom part is just all four factorial, right? So I cancel those two out, and then I'm just left with six and five on the top. And two factorial is just two, right? So I can divide that by the six. And then I'm just left with three times five, so that's just going to be 15. And then I can do like the same four factorial thing canceling with eight, but there's going to be a little bit more terms for eight. So I'm going to have eight times seven times six times five. And then four factorial is 24. So I can cancel this out with a six, and I have a three on the bottom, and then or wait, I have a four on the bottom, sorry, because it's 24. And then I can cancel this out with the eight, and then I have a two on the top, and then I have two times seven times five, which is just 70. So then I have 15 over 70. I can take out a five from top and bottom, and then I have three over 14. And yeah, you do have to calculate the factorials by hand since this is sprint and you don't have a calculator, but this is not too bad. And then look here, and yeah, 3/14 is the correct answer. Anything you want to say for that one, though?
Oh, not really. Yeah, this is kind of just. Yeah, this isn't really that complicated, so.
Yeah. Okay. Uh, do you want to take over here, or do you want me to keep going?
Yeah, I can take over if you want.
It's up to you.
Okay. Give me a second. I have the wrong contest pulled up.
Okay. Is it gonna be a long second, or just like not a long second?
I just have to open a
'Cause I
different
could.
link.
Okay.
We're good.
Yeah, I'll stop presenting that.
Oh boy. Okay, so we're going to be on number 20. So, number 20, if n is an integer such that 2 is less than or equal to n less than or equal to 2010, for how many values of n is 1 plus 1 half times 1 plus 1 third times so on and so forth until 1 plus 1 over n equal to a positive integer. So, for a question like this, we just want to like try the first few numbers first. So if we look at the first few numbers, it'll be 3 halves times the next one will be 4 thirds times 5 fourths, and immediately you can see a pattern, right? These will just cancel out. And so what you're always going to be left with is going to be 2 on the bottom. And then on the top it will be whatever you end on plus 1. So it will be n plus 1. So we're basically looking to make this. We're basically looking to make this a integer. So n plus 1 has to be even. So n plus 1 has to be 0 mod 2. N plus 1 has to be even. So for n plus 1 to be even, n just has to be odd. So we're just looking for how many odd numbers there are between 2 and 2010. So between 2 and 2010, there are. So from 1 to 2010, there are. Between 2 and 2010 is 2009 numbers, and because it starts and ends on a even number, there's going to be 1005 even numbers and 1004 odd numbers. So our answer is going to be 1004. And if we look, that was question 20. Okay. And yep, that's our answer. 1004 values. Okay, number
Yeah, so
21. Okay. Yeah.
yeah, for that one you just had to like just find the really nice pattern where you can like cancel out everything. And to find patterns like that, you like a lot of the time you just want to try like looking at like what the terms like actually are. So like putting all the terms into one fraction was good, and then yeah, you can see the pattern in that way. So yeah, like I don't know, like a lot of the time you just want to like test out your terms and see if you can find a pattern.
Yeah, if you have what seems like a long stuff you have to do, that's very repetitive. You should like try to do at least the first few to see if you can see a
Yeah,
pattern.
like yeah, so like especially when you have like a long like sequence of terms, like maybe addition, maybe multiplication or division or something, that gives you a clue that you might be wanting to look for patterns. And also like um also if you have like the endpoint is like to some like to something of n, and then you're looking for it like you're looking for something over like an interval of n, like that also tells you you also probably like are looking for a pattern to simplify the thing a lot.
Generally, just like something where you have to do something, and it looks like you're going to be using like a lot of repetition in that thing, doing it. Okay. Number 21. If the diameter of a right cylindrical can with a circular basis is increased by 25%, what percent should the height increase in order to double the volume of the original can? So, sorry. So, if let's think about like the equation for like a cylinder, right? Um, the equation for a cylinder is the equation for the we're looking for volume of cylinder is just pi r squared h, right? So here since we're looking for since these two cylinders are similar, we can basically just like we can just look at the ratios of each of these like terms. So pi stays constant, so we don't care about pi. Since we're just looking where the we're working with the ratios between the two cylinders. So, and we're increasing the diameter by 25%, which just increases the radius by 25% too. So we're basically multiplying it by 1.25 twice. So 1.25 times 1.25. Let's put this in fractions. Makes it a little bit easier to work with. So 5 fourths, you get 25/16. So just by increasing the diameter, you're multiplying by the area, the volume by 25/16. 25/16. So now we're looking for how much we need to multiply the height by. So by what percent should the height be increased? Sorry, in order to double the volume by the original cam. So like basically times new height equals 2. So that's not that bad. You just divide it, I guess. Divide 2 by 25/16. So you get. So the new height should be what? Um, should be 32/25. And we're looking for how by what percentage should the height be increased. So how much this is over 1. So minus 1. That gives us 7/25. And this is equal to 28%.
Yeah, and when Bill writes like new height there, he specifically means like
Okay, yeah,
the
like new
factor
height
that you're
over
multiplying by.
old height,
Yeah.
basically.
Yeah. Yeah, basically.
Yeah. Okay. Is there anything else you want to say?
Um Also for I don't know, like doing this like for people that already like kind of know these kind of problems is fine, but also like for the people that might not know these problems initially, I think it's also helpful if you like show it in terms of like R naught and stuff. So like I like to have like my initial volume be pi R naught squared times H naught. And then I like to show like my new radius is going to be like it's going to be 1 point or it's going to be 5 fourths times R naught, and then my new height I would call it like H equals like X times H naught, and then I put that into the volume formula again, and then I would make my volume formula equal to like 2 times V, and then I would substitute V for like all of the R naught and H naught stuff, and then then I can show like all the R naught squares and H naughts cancel. I don't know. I just like to show that for people that uh, don't initially like know the problem. I guess that's not that aren't really familiar with this, but I don't know.
Okay.
It's probably fine.
Alright, problem 22. Side AB of a regular hexagon ABCDE is extended past B to point X such that AX equals 3AB. Given that each side of the hexagon is 2 units long, what is the segment length, segment FX? Express your answer in simplest radical form. Okay, let's draw a regular hexagon. I'm no better at drawing this than Austin is, so amazing. Okay, A B C D E F, and we are extended past B to point X such that AX equals 3AB. So AX going to be somewhat like here. Here's X. So this is going to be 1, this is going to be 2. Given that each side of the hexagon is 2 units long, so each side is actually 2, so like this, we are looking for the length of segment fx. So fx is going to be like this. So we know that ax is 3 times ab, so ax is 6. af is 2. So this question is like begging you to use law of cosine because think about it. We know this is 120 degrees because it's a regular hexagon. We know this is 120 degrees. And we know this side, we know AX and we know AF, and we're looking for FX. So we basically know everything we need to just do law of cosine. So let's just do law of cosine. So fx squared equals 36 plus 4 minus 1 half times 2 times 6 times cosine 120, which is negative 1 half. So fx squared equals 40 plus, these two cancel out, this negative and this negative ends up plus 12. Fx squared equals 52. Fx should be square root of 52 equals 52 is 4 times 13, so 2 square root of 13. So our answer should be 2 square root of 13. And yep, that's our answer. So yeah, this problem is just identifying that the problem has given you everything you need to do law of cosine, like all the conditions you need to do law of cosine. Yep.
Yeah. Yeah, this is just law of cosines. Just like know how to apply law of cosines and like also be able to identify um when you can use law of cosines. Yeah, yeah, this was just like identifying and using law of cosines.
Yep. Oops. Did not mean to do that. Okay. So 23. Charlize accidentally omitted two consecutive integers when adding the elements of the arithmetic sequence 1, 2, 3, so on and so forth until n. If the sum she obtained is 241, what is the smallest possible value of n? So something to think of here is that every odd number, every odd number, you can obtain every odd number. You can express what I'm trying to say is you can express any odd number um as the sum of two consecutive integers. Because two consecutive integers, the one is going to be even, one is going to be odd. So when you add them together, it's going to be odd. And like if you have an odd number, you can basically subtract 1 divided by 2 to get the even number, plus 1 to get the other odd number. And then we can just get two consecutive odd numbers. So as long as the value of n, like as long as for any n number, like as long as the sum of the sequence has an odd difference between itself and 241, like it's going to work. So we basically just want to find n such that the sum of the sequence will be greater than 241. So we can just try some numbers. And this is kind of easy because it starts from 1, so we can just do n plus 1 over 2. This is the kind of quick and easy formula for arithmetic sequence starting that just like 1, 2, 3, 4, 5 all the way up to n, the sum of that sequence. So we can try some numbers that we think may work. So let's try 20, 21, 2. This ends up being 210. So this gets us very close. So this is all the way up to 20. So if we add another number, so we add, say, 21, because that's the next number. It'll be 231. If we add 22, that'll be 253. So this, 253, this is 253 is over 241. But if we look, 253 minus 241 is 12. And 12 is an even number. You can't get to an even number. There's no possible way of obtaining an even number through adding two consecutive integers. So we can't have that. So if we add go to n equals 23, we add another 23. We get 286. 286, you can get a you do have a odd difference, which is 45. So that way you can express this 45 because she omitted two consecutive integers. So the sum of the integers she omitted will be 45. So you can express this, which is pretty easy. It's just 22 and 23. So what is the smallest value of n? N would be 23. And yep, that's our answer. Anything you want to say, Austin?
Um, I think you said all that I wanted to say, or I think you said it pretty well. So yeah, nothing
Okay.
to add.
Okay. Question 24. An audience of 450 people is seated in an auditorium. Each row contains the same number of seats and each seat in the auditorium is occupied. With 3 fewer seats per row and 5 extra rows, the same audience could still be seated occupying all seats. How many rows does the auditorium have? So, the more systematic way of solving this would just be like through algebra, right? So, we would have 450 equals um right. So you get xy equals 450, and then 450 equals x minus equals x minus, what is it? Right, x minus 3 and y plus 5. And like you can solve it, you can definitely solve this just by let's see, what is it? 450 equals xy minus 3y plus 5x. Uh, yeah, and then since xy is 450, you can plus 450, plug 450 in here. These two will cancel out, so you get 0 equals negative 3y plus 5x minus 15. So you get 3y equals 5x minus 15. Y equals 5 over 3x minus 5, and we can put this back in here, I guess. X 5 over 3x minus 5 equals 450. 5 over 3x squared minus 5x equals 450. 5 over 3x squared minus 5x minus 450 equals 0. Quadratic formula. 5 plus or minus square root of, actually, we can multiply all of this by 3 just to make stuff a bit easier on the eyes, maybe. A bit easier on the eyes. Uh,
You can also divide everything by 5.
I could divide it. I could divide everything by 5, multiply everything by 3. Yeah.
Yes.
So you end up with x squared minus 3x plus 2. Oh, sorry, my bad. It should be a minus 270 equals 0. So you get 3 plus or minus square root of 9 plus 4 times 270. That will be 1080 over negative
I mean, you can also
270.
just
What?
you can also just think of factors of
Oh yeah, that's true. I can just think of factors
270.
of 270. Yeah, this is like,
Or you could
actually,
do like that if you want.
yeah, yeah. Okay, I was gonna get to that. Okay, okay. So I was gonna do us more systematically. Okay,
Sure, sure, sure.
okay. So now we just want factors of two. Now we just want to like solve this quadratic and solve it by factoring or quadratic formula. If you factor this, you'll get it's x minus 18, x plus 15.
Yeah.
So x equals 18 or negative 15. And so x is going to be equal to 18. And since x is our row here, wait, is x our row? No, x is the c's per row. So the row would be just or sorry,
And
equation right here.
divide it.
Right. So it's going to be 25. Y equals 25. So we have 25 rows. Uh, right. So that's like how I guess you would like more systematically do this, but that wasn't really how I did it. Um, so how I did this was kind of just thinking about it. Just like to get to 450, or your original like seats and rows, it's going to be one number like times another number to get to 450, right? And the next one to get to the other number, you're it's going to be like this minus 3 and b this plus 3 b minus 5. So you want to think of factors of 450 where like two factor multiply to get to 450, but also if you like change those factors, uh you would also get to like both of them also multiply to 450. And I guess this is just kind of like how familiar you're with numbers, but if you like think about it a bit, for like you have to get a number where it itself is a factor of 450, and when you like when you add 3 to it, it's also a factor of 450, or like when you subtract 5 to it, it's still a factor of 450. So if you think about it that way, after like just a couple of trials and errors, you get 18 times 25 is 450, and then 15 and 20. I don't 15
You can also, yeah, you can also just kind of like list out
like
factors of 450, and then it's kind of easy to see it that way. Yeah.
yeah
Like you can list out like pairs of factors and then just see like which two pairs are like, that scale of each other.
yeah okay. The sides of triangle CAB are in the ratio of 2, 3, 4.
Or
Segment
did he did
PQ.
he check did he
Oh,
check the correct answer though?
did I?
Gotta make sure.
25 rows. I think we got 25. So, whoops. Okay. Four standard six-sided dice are to be rolled. If the product with their values turns out to be an even number, what is the probability that their sum is odd? Express your answer as a common fraction. So this involves like a bit of logic, I guess. A bit. Uh, if you do math, you're gonna come across like a lot of logic. Yeah, we've pretty much done all the stuff from before.
Yeah, or like I think we've done 2017 and then all the years like up to that. So 2017,
Yeah,
2016, 2015, and then now we're on 2010.
yeah.
And why we didn't do like 2018, or I'm not sure if we did 2018, but like why we didn't do like 2019 or 2020, because it was because we think like some people might have already self-practiced with those tests. So we didn't want to do it if like, some people already did them by themselves. But also like if you guys want, you guys can also request like us doing like a year, like maybe like 2020 or 2019. We can also just do that.
Also, like for math counts, like we haven't noticed that much of a change between years. Like if you're going like a bunch of years, there might be like some change in like the stuff they have and like the testing and tests, but like we haven't noticed like that much of a change. It's not that
Yeah.
significant of a change where it stops where the test stops being relevant.
Yeah, for now, like these 2010 questions are we think they're still pretty relevant. So
Yeah,
yeah.
so we are still gonna do them. So yeah, 26. Four standard six-sided dice are to be rolled. The product their value turns out to be an even number. What is the probability that sum is odd? So this kind of involves a bit of logic, where it's So this is asking if the product. So what is the probability that the sum is odd, given that the value is an even number, that the product is an even number. So if so, how to do this? So in logic, you do this by you take the probability of them both. So if so, let's say I'm gonna do a bit of an abstraction, generalization a bit. So if say we're doing P given Q, so P given Q, that's denoted by P given Q. So
Well, you should say like you should have like a P on the outside of it, like the probability of P given Q.
what do you mean by that?
Or I guess you can also say the sample space, but like specifically we're looking at the probability here.
Right. Okay.
So also I like to say like A and B instead, but whatever.
Okay. I've always done P and Q, but A and B is fine too. Sure, we can do A and B. I don't remember where I started using P and Q. I feel like I've seen P and Q used more than A and B, but
Or I use capital A and capital B, but it's
oh,
whatever.
sure. Capital A, capital B. So A given B. So to get this is equal to A and B over A. Sorry, A and B over B. So the probability of A and B both occurring over the probability of B occurring.
But yeah, you can also have like you should also put like P parentheses over like each of those. That just shows like probability.
Right. Yeah. But okay.
Sure.
Sure. Yeah, I can do that, I guess. Okay. So in this case, we would do like the probability that the product is both an even number and is odd over the probability that it's an even number. So for it to be an even number and for it to be odd, um, and for the sum to be odd, out of the four dice, we would either have to have one dice be even, three to be odd, or three dice to be even, two to be odd. That way, not two. My bad. One to be odd. And this way, this product will be even, and this way, the sum will be odd. So, if you think about it, the chance of getting an even and odd number will be the same, right? So, in total, the possibilities are actually we can just calculate each of these individually. That's fine too. But yeah, so the possibility for this will be just four because there's four places the one even dime can be. The one even dice can be, oh my goodness, the one even dice can be over the total chances, which is 2 to the 4th, so 16. So you end up with 1/4. And if you think about this one's basically just this one, but you swap out the even and odd numbers. So it's 1/4 also, add them up, 1/2. So that's probability on top, 1/2. So now we look at the probability that it's an even number in general. So for it to be an even number, it has to have like, for it to be an even number, it it has to have okay, an even number has to have just at least one even number. So for it to not be even, it has to just four odd numbers. You have to roll four odd numbers, so that's a chance of 1/16. So for it to be even, it's just 1 minus 1/16. So you get 1/2 over 15/16, and you end up with 8/15. That's your answer. And yep, that's your answer. 8/15.
So
Yep,
yeah,
that's your answer.
yeah, if you already know like the probability of like A given B formula, you should probably know because like uh it shows up like somewhat frequently. And yeah, and then once you have that, then it's pretty easy, just like just regular probability stuff.
Yeah. Okay. So Annie, Ben, and Claire are training for Mathcounts on January 1st. They started to solve a large packet of problems that their coach gave them. Each of them worked at a constant rate. Annie solved 6 problems each day and finished 4 days after Ben did. Claire solved 3 more problems each day and Ben did Then Ben did and finished 2 days before he did. How many problems were in the packet their coach gave them? Austin, I don't think I did this problem. Did you do this problem?
Okay. Kind of. It was kind of in a rush.
Okay.
Uh,
Uh,
yeah, it was the last problem that we did, I think.
yeah.
Yeah.
Okay.
Or I just
I
said
didn't really.
like,
I don't think I finished this problem. So.
so I just said
Mhm.
like if you just give like variables to like two of these quantities,
Yeah.
then you can just solve it by algebra.
Right. Yeah. I
So
was trying to.
specifically, I said D, variable D,
Mhm.
as the number of days that Annie took to solve her problems.
Okay.
And then I set the variable B as the number of problems that Ben solves each day.
Okay.
And then I could just solve all of it by algebra.
Right. Yeah. I was trying to avoid solving it by algebra, but okay.
Oh, well, I mean, I don't know how else would you it just seems like,
Well,
just
that's
had
what
to
I
be
was. That's why I was. That's why I didn't finish solving the problem. I was too hard, trying to avoid solving it by algebra. Okay.
okay.
But yeah. I want to try doing this. I want to do this if we were gonna do it by algebra. I just want to do this with them. We can do d equals. We can let d be bin days and
Ben state. Okay.
bin days. That extra apostrophe s is too hard. And then what do we? What other? We can do p. Sure. P equals bin's problem per day. Problem per day. So d times p will be equal to 6 times will be equal to 6 times p. Oh wait, my bad. 6 times d plus 3. That's for oh, that's for Annie, and then also equal to p plus 3 times d minus 2. Right? Yep. Okay. So let's see. Yeah, I guess just take any two of these. You can make a system of equations. We can expand this. This expands to pd plus 3d minus 2p minus 6. Uh, and then I guess do, we can put this in here, I guess. We can do 60 plus 18 plus 3d minus 2p minus 6 equals dp. Actually, do even one.
Or you can also you can take
Oh,
you can take dp equals like the last part and then
this far.
the pd dp cancels.
Oh, right, yeah. That's a good point. I literally did that like a couple questions ago. I don't know why I didn't think of this. Yeah, and I guess you can just do a relation between these. D equals 2 over 3p plus 2, and then we can put this literally anywhere. Uh, where do we put it? We can put it here, I guess. P plus 2, P equals. Actually, it might be better if we express P in terms of D, because we have a D thing here. So if we express P in terms of D, we have P equals 3 over 2D minus 3. So we plug that in. We get D times 3 over 2D minus 3 equals 6D plus 18. Expand this a bit. D squared minus 3D equals 6D plus 18. I guess you can divide everything by 3 and multiply by 2. So if we do that, we get D squared minus 2D equals 4D plus, what's this going to be? 12. D squared minus 6D minus 12 equals 0. And it's going to be D Wait, is this even factorable, Austin? Austin, did I do something wrong? Because I don't think this. I
Uh,
don't think this gives an integer factor.
oh wait, I think I was solving this problem, but like I didn't completely solve it. Like I was also
Oh
like,
wow,
wait,
good job,
like
Austin.
yeah,
Good job.
yeah. This was the last problem we got
Do you
to.
see
So,
anything I did wrong here?
uh, well, what if it is not an integer, but like
Well,
when you product it, it is.
oh, that's a good point. That is a good point. Okay, we can try that.
Since we
So,
we both got non-integer answers, maybe
right,
that
okay.
is.
So, I just quadratic formula then. I don't think
But I
that's the
mean,
case, Austin. I don't think that's going to be the case.
yeah, but then you should have some like radical term, right?
You're going to have some radical term. It's going to be some radical term like
Hmm.
minus an
I
integer.
guess we both just did it wrong now.
There's going to be some radical term minus an integer. That's not, when you multiply those together, that's not going to give you an integer.
Yeah, I know. Uh, hmm. Uh, your second equation thing is for
Oh,
Annie, right?
yes. Did I do it
Shouldn't it
wrong?
be D plus
Oh,
4?
oh, yikes. Indeed, it should. So this actually doesn't affect much, I don't think, because we've only worked with this. So only this what bit is affected. So this should be 6 times 4, 24, 24. Do the same thing. D squared minus 2d equals 4d plus. Is it a plus? It is a plus. Plus 16. Okay. So now let's see. D squared minus 6d minus 16. See, this is actually factorable into integers. You get d plus 8, d minus 8. I meant d minus 8 and d plus 2 equals 0. So d is going to be equal to 8 because they're not going to do this in negative days. So d is 8. We put d back into wherever we were, so right here, and we get p is equal to 9. So 8 times 9, that's 72. 72 should be your answer. Check. Yep. So I guess, Austin, you just did something wrong with your
No,
calculator.
or yeah, I did something wrong the first time, and I remember like I found my problem. It was also something like with doing like the days wrong or something.
Okay.
And then I was yeah, I did like I did plus 4, but it was like supposed to be minus 4 in my situation. And then I was like going to do it like that, but then I had to go for like science pool.
Okay. It's 9:39. Do you wanna?
Yeah, we can end it here.
Okay.
Okay. All right. Thank you everyone for coming to our math council meeting. So actually, so me and Bill are going to be a little bit busy right now. Just with like
Stuff.
with our AP tests like UIL State, and I have National
Yes.
Science Bowl.
Yeah.
Um, and yeah, also for like our AP tests, we've kind of
Yeah.
procrastinated them a
So
lot with
it's kind of like
not.
learning the entire year in like a month, basically.
Yeah. So we kind of need some time for ourselves just to like study for that self. So unfortunately, we're gonna have to kind of like hold back on our math counts meets for about like a month or so.
Yeah.
Um, so my national science bowl is gonna be like the latest out of all of this, and it's gonna end on the 22nd, which is a Saturday, or May 22nd, which is a Saturday. Um, and so with math counts, I think we can probably continue back on the 23rd, which is a Sunday. So yeah, it's going to be like a month until we can come back and do these Mathcounts meetings. So yeah, we're sorry to say that, but yeah, we're going to need to do that.
Yeah.
And yeah, we'll also announce this on our Discord and Google Classroom.
Yep.
Um, yeah, anything else you want to say about that, Bill?
Uh, yeah. I know.
Okay,
We're just
okay,
gonna
yeah,
be away for a bit to like have some
yeah,
more time to work on stuff.
for some bit, yes. All right, so that's gonna be it for this meeting. We hope you learn some stuff. Okay,
Bye.
and yeah.